In the last few weeks, we have examined two calculi that have attempted to represent uncertainty in rule-based expert systems. This week, we take a look at fuzzy logic, which, rather than representing uncertainty as such, instead models the concept of vagueness. It was first developed by Lofti Zadeh back in 1965, and he is generally considered to be the father of fuzzy logic. Or really, that should be fuzzy sets and fuzzy logic. Zadeh's idea was to consider sets of items where, instead of an item being definitely in the set or out of it, it has a degree of membership, a score if you like, which tells you to what degree the item is in the set. Consider the statement that you see on the screen. Most Dutch people are tall. Well, how tall is tall? We would probably regard a man who is 6'5" as tall, but what about someone who is 6 foot? What about 5'5"? What proportion is most? Technically, it's anything above 50%, even if only by a hair's width. But for most people, most will constitute a much higher percentage, like 80% or so. Zadeh's idea was to consider the set of objects or people or whatever described using such vague terms as tall. The set of all tall people, if you like. Instead of being either in or out of the set, people would have a degree of membership, ranging from 1, meaning definitely yes, down to 0, meaning no way. If Sam is 6'8", then his degree of membership in the set of tall people would be 1. If Sam is only 5'8", then his degree of membership will be much lower, say 0.3. Perhaps his wife, who is only 4'8", thinks he's tall, but very few other people do. The lines on the screen indicate what my personal idea of tall and most are. Below a certain level, the degree of membership in the sets of tall people, or counts as most, is 0. These are the values that are definitely out of the set. Above other values, the degree of membership is 1, with a sliding scale in between. The ranges you would have chosen might be different, but you get the idea. Fuzzy logic follows the same procedure as normal logic, except it replaces simple true-false values with degrees of membership in the various sets concerned. Before we can apply any fuzzy logic, we have to turn statements such as Tim is 5'8" into statements such as Tim has degree X in the set of tall people, Tim has degree Y in the set of medium height people, and so on. We have fuzzified his height. In the example shown on screen, we have divided up the entire height range into 3 fuzzy sets, and Tim gets a degree of membership in each of them. Alternatively, we might only need 1 set, for tall people, say, in which case Tim will be reduced to just 1 number instead of 3. An expert system consists of a series of if-then rules, and these are very easy to deal with in fuzzy logic. The degree of membership associated with the premise of the rule, the if part, becomes the degree of membership of the conclusion, the then part. Take the rule that you see here. If the score associated with the statement the animal has forward-pointing eyes, or the degree of membership of the animal in the set of those with forward-pointing eyes, if you like, is 0.8, then that becomes the score associated with the conclusion the animal is a carnivore. The animal has degree of membership 0.8 in the set of carnivores. If the same conclusion appears in more than one rule, such as the animal is a carnivore, then that is equivalent to a single rule with the 2 premises joined by or. In the example on screen, common sense suggests that the 2 rules given can be combined into one, namely that the animal is a carnivore if it has forward-pointing eyes or it has sharp claws, or both, of course. We'll be seeing how you implement operators such as and or in a moment. Of course, since the concepts in fuzzy logic are necessarily vague and imprecise, the rules themselves tend not to be clear-cut. Take the 2 rules at the top of the screen. One informs us that the presence of a certain symptom indicates a bacterial disease, while another symptom indicates a viral disease. What if both these symptoms are present? Wouldn't these 2 rules conflict? Well, yes and no. It's true that the rules tend to push in different directions, as a particular disease cannot be caused by both a virus and a bacterium, to the best of my understanding. But there's no inherent conflict in fuzzy logic here. The classifications bacterial and viral are maintained as 2 separate fuzzy sets, and each rule only affects one of the 2, ignoring the other. Similarly, look at the other rule I've given. If the rotor speed is high, then the fault is unlikely to be in the compressor. The problem here lies in how we implement the term unlikely, and yet it is the very sort of vague term that fuzzy logic was set up to deal with. Firstly, we have to decide on a score value for unlikely, however we intend to interpret that score. I suggest that a value of 0.2 or 20% is suitable to represent unlikely. One possible approach would be to establish a set termed compressor fault and assign the identity of the fault to it, i.e. we are trying to diagnose a particular fault and it can be in various components of the system, one of which is a compressor. The rule would conclude that, if the rotor speed were high, then the degree of membership of the variable fault in the set faults in the compressor is only 0.2. The problem is that the premise is itself vague. Suppose the rotor speed has a degree of membership of 0.7 in the set high. How would this affect the degree of membership of fault in the set faults in the compressor? Well, you could always use some sort of mathematical formula to adjust that 0.2 value somehow, but that wouldn't be especially satisfactory. After all, a lower rotor speed doesn't mean that the fault isn't in the compressor. One way round the problem would be to have a variable compressor fault and several sets such as likely, definite, unlikely, and so on. In that case, the score of 0.7 for the rotor speed establishes that compressor fault has a degree of membership of 0.7 in the set unlikely. In this case, we don't need to establish a numerical value for unlikely at all. However, neither of these solutions strikes one as being particularly elegant, and the best strategy when faced with a rule like that will be to rewrite it to remove as much ambiguity as possible. Just as with Boolean logic, we require the ability to perform AND, or NOT operators. There aren't any hard and fast rules for doing this, but here are two methods commonly used. Both are intuitively acceptable, and neither has any particular benefit over the other. The simplest form is the so-called Zadeh operators. AND requires both its operands to be true, so x and y becomes the minimum value of x and y, assuming that x and y are the appropriate degrees of set membership. The OR operator is less particular. It only requires one of its operands to be true, so we replace it with the maximum value of x and y. Similarly, NOT is the inverse of x, so we replace x by 1 minus x. If Tim has a degree of membership 0.2 in the set of tall people, that is equivalent to a degree of 0.8 in the set of people who aren't tall. The other commonly used version is based on multiplication, in a similar way to probability. X and y becomes the product of the degree of memberships in the two sets. If Tim has a degree of 0.2 in the set of tall people, and a degree of 0.4 in the set of rich people, then Tim's degree of membership in the set of people who are both rich and tall, internet dating site algorithm anyone, is 0.2 times 0.4, i.e. 0.08. In this calculus, we keep 1 minus the degree to represent NOT, and from this we can work out the formula for OR using the logic shown. Pause the video, and you'll see that the logic does actually work. We end up with a formula that, again, looks very much like OR in probability. Right at the very end, once all the rules have been processed and all the logic worked out, we have to turn the results back into something we can present to the user. In terms of fuzziness, we have kicked the can as far down the road as we can, but the time has come to start putting actual numbers to these concepts. Of course, we could always duck the problem and simply display the various degrees of set memberships as they exist. Let the user interpret them as best he can. Looking at the table on the screen, we can see that the fault we're trying to diagnose is probably in the compressor, although there's a substantial chance that it lies in the suspension. At this point, we'd send off an engineer to check on both of those. Assuming that we did want to turn the degrees of set membership back into crisp, i.e. non-fuzzy numbers, then there are probably as many ways of doing it as there are fuzzy logic systems out there. Here we have the various sets indicating the chance that a prospective employee will be hired, together with a degree of Tim's membership in each of the sets. The vertical lines indicate the central values of each of the areas. One rather crude way of assessing Tim's chances is to multiply the degree of membership in each set by the percentage likelihood for each of those sets. More sophisticated variations on this approach involve more complex mathematics that take into account the various shapes of the sets. We've drawn them as nice, neat trapezia, which have an easily defined central point, but if they have irregular shapes, we would have to replace that with what you could term the centre of gravity of each region. Ironically, the process of defuzzification is itself rather fuzzy and ad hoc, involving quite a lot of hand-waving. Try to find a real-life system that uses fuzzy logic and see how it produces definite values at the end. Speaking of which, here are 3 areas in which fuzzy logic is appropriate, picked fairly at random. I'm sure when you go on the internet you'll find others. Indeed, I was spoiled for choice. I've ignored the large number of examples that I came across from more than 10 years ago, and concentrated on fairly recent examples. There's a fuzzy set if ever you came across one. What is the degree of membership of these publications in your idea of the term recent? Anyway. Das, Guer and Dutter list various examples in which fuzzy logic is applied to medical diagnosis. Doctors often diagnose disease based on impression and observation, a process which naturally lends itself to vagueness, and therefore fuzzy logic. Dixit and Singh describe a system that detects cracks and other damage in structures using what they term soft computing, which is another term for fuzzy logic. Finally, and bang up to date, M. Ram, in his book Advanced Fuzzy Logic Approaches in Engineering Science, collects a large number of practical examples where fuzzy logic is used in the real world. It's a rather pricey book, that one, so you might like to try getting it on interlibrary loan. And there you are, a quick tour around the subject of fuzzy logic. In the next lecture, we start a completely new and far more interesting topic, game playing.